All right. Welcome back again, everybody. Today we're going to be doing the last section of chapter 6, the last section of the trigonometry chapter, and this one is all about solving trigonometric equations. I wanted to save this section for the end because it's a little bit more gentle than some of the previous sections, and it's also one of the skills that you're really going to need right when you go into Calc 1. So I expect all of you to immediately take Calculus 1 after this class. Although maybe after a break, take it next semester or something like that. Don't feel like you need to cram it in. But yeah, this is a good place to end the trigonometry chapter and a pretty good place to end the course as well. And then you'll be well prepared for Calculus 1. All right. Let me pull up the slides and we will get started. Another good news about, or good bit of news about this section, it's not nearly as long as the last one, and you've been well prepared for it, so it's pretty fun. Okay, here we go. The overview is this. We're going to talk about just solving trigonometric equations. We're going to solve them in linear form. We're going to solve them in quadratic form, and we're going to solve them using identities. And then I'll give a little note about solving them using a calculator. One little note about this section also, it's basically just all examples. I don't really have a ton of like intro or disclaimers to give. We're just going to jump right into examples, okay? So this is a great one to get your hands dirty with, and we'll get our hands even dirtier when we're doing the activity, all right? So jumping right into it, uh, let's do this. Let's solve the equation cosine of theta equals 1/2. Yes, that's it. Well, here's the thing. The domain of cosine is all real numbers. So this equation actually has infinitely many solutions, right? There are infinitely many angles that will give you a cosine value of 1/2. But remember that cosine is also 2 pi periodic. Its period is 2 pi. So that means there will be solutions in the interval 0 to 2 pi, but there are going to be solutions outside of that interval as well. And what's nice is that those solutions will also have a periodicity to them, depending on what we're solving. And we're going to see that throughout the whole section. We'll see that periodicity in our solutions. So, first of all, in the interval 0 to 2 pi, if cosine of theta is 1/2, then the angles that will satisfy that are pi over 3 and 5 pi over 3. And again, you can imagine the unit circle. We're going to do that a lot. Imagine the unit circle. Cosine is 1/2, so we're looking at a cosine value of 1/2. So there's this angle right here, which is going to be pi over 3. And then there's this angle down here, which is 5 pi over 3. So those are the two angles in the interval 0 to 2 pi that have a cosine value of 1/2. All right. We can even see this geometrically if we look at the graph of the cosine function. So here, actually, I guess I should have labeled this theta, but yeah, it's the angle, right? So this is the angle, and this is the cosine curve. And if we draw the line y equals 1/2, then we can see those intersection points of the cosine curve and the line y equals 1/2. And the inputs that are associated with those intersection points are the solutions we just found. So there's the geometric interpretation of that algebraic result right there. Okay. However, remember the graph keeps going. So we're going to have, it keeps going in both directions, in fact. So we're going to have a lot more solutions than that. So if we want to solve it in general, we need to account for those. And in this case, what we're going to do is we're just going to add integer multiples of 2 pi to each of these solutions, and that'll give us another solution. Yeah, it's just going to give us another solution because cosine is 2 pi periodic. So more specifically, for all integers k, these are the general solutions to this equation. Theta equals pi over 3 plus 2k pi, right? Even multiples of pi. And theta equals 5 pi over 3 plus 2k pi. And those will give you all of the different solutions to cosine of theta. Notice there are infinitely many of them because there are infinitely many integers, right? So if you basically increment k or decrement k, you'll get another solution to that equation. Here I've got a table of some of the solutions. So here is that first general form. Here's that second general form. And here I've got different values of k chosen. -2, -1, 0, 1, and 2. And when we plug those values of k into these, we're going to get another solution. So -11 pi over 3, -7 pi over 3, -5 pi over 3, -pi over 3. These are the ones we found initially, right? Pi over 3 and 5 pi over 3. That's when k is equal to 0. Those are like the initial solutions. When k is equal to 1, we're adding 2 pi to pi over 3 to get 7 pi over 3. And we're adding 2 pi to 5 pi over 3 to get um, pi over 3. Wait a second. That doesn't seem right. Oh, I'm sorry. I'm sorry. Wait, I think I got lost here. 7 pi over 3, 5 pi over 3 plus 2 pi. Hang on a second. 12 pi over 3. Yeah, sorry. That should be 13 pi over 3 if I'm not mistaken. Let me calculate it real quick. Um, oops. 5 pi over 3 plus 2 pi is going to be, let's see, 2 pi is 6 pi. Oh, it's okay. 6 pi over 3. That should be 11 pi over 3. My bad. There you go. 11 pi over 3. I'll fix that after the recording. Okay. And then on and on and on. Oops. And then on and so on. So you can keep going either direction, negative or positive. And then here's another geometric interpretation of that. You can also use Desmos. You can graph these things in Desmos, graph y equals cosine of x, graph y equals 1/2, kind of like we've seen in the past. And just click on these points and it'll show you what those intersection points are. And here you can kind of see some of them just in this interval from -2 pi to 2 pi. Okay, now let's do another equation. Let's try this one. Solve the equation sine of 2 theta for 1/2, or 2 theta equals, sine of 2 theta equals 1/2. This one, well, okay, try this one on your own, but I'll give you a hint in a minute. So first I want you to just think about it for a sec. Solving that equation. Okay, now I want you to verbalize something. Remember, you can say it to yourself, your dog, your cat, your colleague, your peer. If you're watching this with somebody, just verbalize something to get your brain thinking about how you could solve this. Okay, now try to work it out, and I'm going to give you a bit of a tip here. You notice you're solving for theta. So be careful when you try to solve this because you're going to have to kind of solve it for 2 theta first. And then once you know what it's going to be for 2 theta, then you can find out what it's going to be for theta. All right, that's my hint. Okay. All right, now let's do this one together. So sine of 2 theta equaling 1/2 means that 2 theta equals pi over 6, or 2 theta equals 5 pi over 6, as long as the angle 2 theta is in the interval 0 to pi, 0 to 2 pi, okay? So there's a reason for this. When you solve this equation, you're kind of using that same argument that we did with the inverse trig functions, right? We're asking what angle has a sine value of 1/2. What angle has a sine value of 1/2? Well, when I imagine the unit circle, okay, imagining the unit circle, if the sine value is 1/2, there's this angle and there's this angle because that's the short leg, right? Okay, so that's going to be pi over 6 and 5 pi over 6. But here's the catch. When we did that, when we were like, what angle has a sine value? The angle we were referring to is 2 theta, right? The angle is 2 theta there. That's why we got this right here. And now here's the catch. If we add integer multiples of 2 pi to each one of these solutions, we will get another solution and another solution and another solution, right? So what we have to do before we do anything else is add integer multiples of 2 pi to those general solutions. So the general solutions, because there's no restriction here, right? The general solutions are pi over 6 plus 2k pi and 5 pi over 6 plus 2k pi. But those are the solutions to this equation, but we haven't solved for theta yet. We haven't solved for theta yet. We just solved for 2 theta. Now that we have the genericity, the genericness, now that we have the genericness accounted for, we can divide by 2. And when we divide by 2, we get these. Yes. So we're taking this equation and dividing both sides by 2. And we're taking this equation, and dividing both sides by 2, just like so. That's it. Now we have the general solutions for theta. So theta is equal to pi over 12 plus k pi, because that divided by 2 is k pi. And theta is equal to 5 pi over 12 plus k pi, again, because 2k pi over 2 is k pi. So these are the solutions for theta. There's a little bit of a subtlety there. And I put this note down here because this is an important point. You've got to include the repeating term before you do any manipulations, okay? And again, that's because it's not a sine of 2 theta that is 2 pi periodic. It's sine that's 2 pi periodic. So we solved for 2 theta initially, and that's where that 2 pi periodicity needs to be applied, right there before we do anything else. Then we can start manipulating stuff. Okay. Again, here are some solutions. Take note of this, right? These are different values of k. Here's theta equals pi over 12 plus k pi. Theta equals 5 pi over 12 plus k pi. And then, yeah, these are all like a table of the different solutions here. I highlighted some of these in blue right here because these are actually the solutions that are going to occur in the interval 0 to 2 pi. So for this equation, if you want to know the angles theta that are in the interval 2 pi, that solve 0 to 2 pi, that solve this equation, it's these four. And let me kind of explain that in an additional example right here. So now this is the same question, but now the question specifies that theta has to be in the interval 0 to 2 pi. Okay, well, we already found the generic solutions. We found the general solutions to this equation in the previous example. Now, if we want to know the angles theta that are in 0 to 2 pi that solve that equation, we're just going to increment k. So starting with k equals 0, we get pi over 12 and 5 pi over 12. Now let k go up by 1. When k is equal to 1, we get pi over 12 plus pi, which is 13 pi over 12. And we get 5 pi over 12 plus pi, which is 17 pi over 12. Now we might have to go further. So if we increment k again and we do 2 pi, we're going to get what? What do we get when it's 2 pi? Let's work that one out together. So pi over 12 plus 2 pi. That's equal to pi over 12 plus 24 pi over 12, right? Just finding a common denominator. But that's going to be 25 pi over 12. But notice this, 25 pi over 12, that's 2 and 1/12 pi, right? 2 and 1/12 pi. So that's already outside of the interval 0 to 2 pi. So we've gone beyond the interval 0 to 2 pi. So that means that when k is already at 2, we've gone too far. We've gone too far. So we're done. These are the only solutions that are in the interval 0 to 2 pi. Of course, there's infinitely many solutions going outside or outward in both directions, but those are not in the interval 0 to 2 pi. Again, let's take a look at a picture of it. So here is a visualization of those solutions. This is the graph of sine of 2 theta. Notice here that there's two periods. Remember what happens when you change that number omega, that changes the period of the function. So here the period is now shrunk. It's shrunk to pi. So you get 1 period, 2 periods in the interval 0 to 2 pi. And these are the solutions to this equation for theta, right? There it is. There it is. In fact, yeah, see, I should relabel these as theta. I'll do that later. There we go. Okay. All right. So now let's do another one. And here's one that I want you to try on your own. Now that we've done it a couple of times and you've kind of seen the subtleties there, try to do this one on your own as well. You want to solve the equation tangent of theta minus pi over 3 equals 1. All right, so ponder that for just a minute. Oops, where are you? There you are. So ponder that for a minute. Okay, now say something out loud. Maybe that phrase that we learned about in the section on inverse trigonometric functions. And then try to work it out on your own. The hint I will give you is that we have not restricted our interval for our solutions. All right, here we go. Let's do it together. So solving this is basically the same thing that we did using inverse trig functions. What angle has a tangent of 1? Okay, well, one solution is pi over 4, right? So right off the bat, we get pi over 4. And that's just going to be in the interval 0 to pi, right? Because that's yeah, in 0 to pi, we get that. Now, tangent is pi periodic, so we're going to have to account for that pi periodicity. But the thing I want to point out, first of all, is we only solved for this being equal to pi over 4, for that being equal to pi over 4. We said what angle, blah, has a tangent of 1? And the answer is blah is pi over 4, right? Blah is pi over 4. Now, because tangent is pi periodic, we need to add integer multiples of pi to that. Integer multiples of pi, just like so, because it's pi periodic. Now that we have made that sum, now that we've added in that repeating term, we can continue the manipulation. So we're going to add pi over 3 to both sides and then simplify, and we get 7 pi over 12 plus k pi. So these are the general solutions to this equation. And again, you just increment k. K is an integer. It could be negative, it could be positive, it could be 0. But every single one of these angles will be a solution to this equation right here. Oops, sorry, it's a typo there too. That should be a 3. There we go. All right. Okay. Now we're going to tweak things a little bit. So we've pretty much just been we've pretty much been solving equations that are like sine, cosine, or tangent equals a number. Now we're going to tweak things a little bit and we're going to look at equations that are given in linear form. Linear meaning in the form y equals mx plus b. So this is one of those equations. Maybe I kind of gave away more than I should have by saying that, but we're going to try to solve this equation, this equation in the interval 0 to 2 pi, okay? And I think you might be able to do this one on your own already. Just keep in mind you are trying to solve for theta, so you might have to massage things a little bit before you start, right? So think about it for a minute. Okay, say something out loud, verbalize it, and now work it out on your own. And we'll do it together in a moment. Okay. All right. So the first thing we need to do is we need to isolate cosine. And I don't know if you can tell right off the bat, but this was kind of me giving it away earlier. This equation is, quote, linear in cosine of theta. It's basically if you treated cosine of theta as like u, then you would have something of the form mx plus b equals 0. Or if you treat cosine of theta as x, you've got mx plus b. So m in this case is 2, x in this case is cosine theta, and b in this case is root 3. So you're pretty much solving a linear equation, except now it's linear in cosine. So these we can solve using elementary methods, right? You basically move everything away from cosine theta, and you're left with this. Now you're in a situation that is equivalent to what we just saw a minute ago in the previous examples. What angle theta has a cosine value of negative root 3 over 2? What you're going to do is imagine the unit circle. So what angle has a cosine value of negative root 3 over 2? Okay, let me think of the unit circle. Negative root 3 over 2, that's the long leg. So cosine's going to be over here. So it could be this angle, or it could be this angle right here. So 5 pi over 6 or 7 pi over 6. And that's it. That's it in the interval 0 to 2 pi, because we have that restriction. All right. Now, here is where things get kind of funny. This is why just remember computers and calculators are just machines. They only do what we tell them to do. So if you tried to use a calculator to solve this, it will actually miss one of the solutions. So caution. If you use the inverse cosine function like on your calculator, or frankly, even just using it here, it's only going to give you one solution. It's going to give you the solution 5 pi over 6. And that is due to the domain restriction required to define inverse cosine, right? It's going to miss the solution 7 pi over 6 because if you remember, we restricted cosine to be in the interval 0 to pi, right? Do you remember that restriction? 0 to pi. Well, guess what? 7 pi over 6 is not in that interval. So a calculator will miss that solution. Algebraically, we would miss that solution if we only relied on this. And that is why that phrase, what angle has a cosine of negative root 3 over 2, is a more powerful, more meaningful way of solving these than just using the inverse cosine function. All right? That's one of the reasons that I wanted to mention it to you back in section 6.7. So use that, but remember, calculators have that domain restriction built in, so beware. All right, now let's talk about solving them in quadratic form. And I won't give any more away than that. I want you to try this one on your own, and then we'll do it together in a moment. So think about it again. You're trying to solve fourth theta, okay? Now, verbalize something. Maybe like, what do you see? What do you think you could do here? All right, now work it out on your own, and we will do it together in a moment. Okay, all right. So maybe because we've seen this type of thing before in the past, you kind of recognize what's going on here. But this equation is, quote, quadratic in sine theta. In other words, it has a quadratic structure, but the variable that we're solving for is not the variable of the quadratic structure. The variable that is associated with the quadratic structure is sine of theta. So for example, if we let u be equal to sine of theta, then this equation, or I should say this expression on the left side becomes this. Oops. Ah, becomes, oh my gosh, becomes this right here. That's it. And now you've got a good old quadratic equation, right? Well, this is a quadratic expression, and you know what to do with quadratic expressions. And if you had a quadratic equation, you know what to do with quadratic equations. There's three ways to solve them: factoring, completing the square, or the quadratic formula. Luckily, this thing is nice enough that it factors. It factors into 2u minus 1 times u minus 1. But you just got to remember, we made a substitution there, right? We're not solving for u, we're solving for cosine, I'm sorry, we're solving for sine of theta. So replacing that, these are what those two factors look like. Now we can set this expression equal to 0. We can use the zero product principle. This being 0 yields sine of theta equals 1/2. And this being 0 yields sine of theta equals 1. There we go. So now we're back to where we were in the beginning of this lesson. What angle has a sine value of 1/2? And then what angle has a sine value of 1? All right, that's where we're at. Okay, so looking at the first equation here, sine of theta equals 1/2 when theta equals pi over 6, or 5 pi over 6. Imagine the unit circle, right? Okay, sine of theta is 1/2. Okay, that's going to be this one because sine is the short leg, or this one because sine is the short leg. That first one, pi over 6, 5 pi over 6. Then we need to add the repeating term, so that's where this comes from. And then we look at the other one. So the solutions to this one, what angle has a sine value of 1? Well, imagining the unit circle, it's got to be this angle right there, pi over 2. Pi over 2. Add 2k pi, and we got it right there. It's that easy, right? Not too bad. This one's kind of cool because I want to take a look at the graph. Remember, there's a geometric interpretation of this here. This is just like this is a graph. You can graph it, and we're looking for the zeros of that graph. And here's what it looks like. So this is a function that's quadratic in sine of theta. And notice you've still got that like sinusoidal behavior. The only difference is we're kind of like adding it. Any of you that go on to study like mechanical engineering, electrical engineering, you're going to see things like this a lot, especially if you ever study Fourier analysis, because that involves expressing continuous functions as sums of trigonometric polynomials, or I'm sorry, as basically combinations of trigonometric polynomials, which is what this thing is here. It's a trigonometric polynomial. But look, let me zoom in down here. There we go. Yeah. Look, those are our solutions, right? Pi over 6, pi over 2, 5 pi over 6. Those are the ones in the interval 0 to 2 pi. And then we have adding 2 pi to get to the next ones, just like that. And it will it will repeat that way forever. It'll repeat that way even beyond what you're seeing pictured here. But those are the zeros that are the solutions to that equation right there, the roots of that equation. Cool stuff. Super cool stuff. Okay. All right, next thing, solving trigonometric equations using identities. To be honest, we've kind of exhausted all of the new stuff that we needed to learn here. Now we're just going to use identities that we know to massage these equations into ones that we can solve the same way we just saw a minute ago. All right. So you know what? Maybe you should try this one. Try this one on your own, and we'll work on it in a second. So think about it. All right, say something out loud. I would say, what identity do you think you could use here? All right, and now try to work it out on your own. Okay, here we go. Um, well, first thing I see is I see a cosine of 2 theta. So I'm tempted to use a double angle identity for cosine. Now, one issue I do see here is I've got a couple options for the double angle identities, right? For identity for cosine. Which one is going to work? Well, I know that, well, I'm gonna need to end up with something that just has one trigonometric function in it. So I got to be a little bit discriminant here. One of those double angle identities looks like this. And I'm gonna choose this one because this side involves sine, and this identity involves sine also. There was the other identity, this one, right? Cosine of 2 theta equals cosine squared theta minus sine squared theta. You could try to use that one, but the problem with that is if you use it, you're still going to be left with a cosine and a sine, and you're not going to be able to rectify it beyond that. At some point, you're going to have to substitute for either cosine or sine to continue on. This one eliminates that problem right away because by using this identity, it rephrases everything in terms of sine. So here we go. Sine, I'm sorry, this is what we started with. Now that I do this, we get that. And now there's only sine thetas. So now if there's only sine thetas, we're going to get this. And once again, we have a trigonometric polynomial. In this case, it's actually quadratic. It's quadratic in sine. It can be factored, thankfully. And it factors like this. Just like before, setting those equal to 0 yields that sine of theta equals 1/2 or sine of theta equals -1. Then we ask ourselves and imagine the unit circle, what angles have a sine value of 1/2 and what angles have a sine value of -1? We know that it's going to be these. And then, well, I guess that's it. We were restricted to the interval 0 to 2 pi, so those are the answers. Those are all the solutions to this equation in the interval 0 to 2 pi. Cool stuff. If we wanted the more general solutions, we would add that repeating term, that 2k pi, because cosine, or I'm sorry, because sine is 2 pi periodic. So if we needed to find the general solutions, instead of just the ones in 0 to 2 pi, we would add 2k pi. All right. Now, last little bit here, solving trigonometric equations using a calculator. This is pretty straightforward. I don't actually have any examples of this because of how straightforward it is. The basic answer is this. If you want to solve trig equations using a calculator, you just use the inverse trig function button on your calculator. That's it. All right. So most calculators have the inverse trig functions programmed in already. However, couple of cautionary notes. One of them is make sure your calculator is in radian mode. All right. Make sure it's in radian mode so it doesn't give you the wrong answers. And then this one, which I talked about a minute ago, remember the restricted domain used to even define those inverse trig functions. Your calculator has those restrictions built in, okay? They're already built in. So if you're using it, if you're using a calculator to solve these things, it may give you incorrect results. It just depends on, or sorry, incomplete results. It just depends on what equation you're trying to solve. So just be conscientious of that if you're using a calculator. Um, and that's pretty much it. Other than that, you just use the inverse trig function button, and that's it. Yep. Speaking of that's it, that is it for this section. That is the end of section 6.9. So I'll leave you with this. What is next? Well, you should check out the supplementary sections, the lectures for section S1 and S2 over the break. Those ones are just for you to watch on your own time over the break. There's a lot of good content there, a lot of good information. It can help you out in your later classes, your major courses. But in general, you should, embrace an attitude of lifelong learning, all right? Just mull over those sections if you'd like. Section S1 is all about conic sections. What I do in that section is I explore the geometry of the conic sections. We didn't really get to explore that as much in the previous sections, but I wanted to emphasize the formulas and the basics of those things to help carry you through calculus. But you should watch section S1 just to see the geometry of the conic sections because it's really, really beautiful. I also derive the formulas for the conic sections in that lesson, the formulas that we saw earlier on in the course. Section S.2, that's all about the law of sines. So in that section, I go over the law of sines. I'll do a bunch of examples of it, so you can check that one out as well, just whenever you get the time, all right? But that is it. That is it, my friends. Congratulations. You've made it through modern mathematical methods for STEM majors. I hope you've enjoyed it. I've enjoyed it. This class is very special to me, and I'm just really really proud of how far you all have come, okay? So I'll leave you with this. Congratulations. You should congratulate yourself. Give yourself a pat on the back. Shake each other's hands if you've been watching these together. I'll leave you with this quote from one of my favorite mathematicians, George Cantor. He said, "The essence of mathematics lies entirely in its freedom." I hope maybe you've kind of seen that over the course of this course. Mathematics is very creative. It's a very exploratory endeavor. It's not just a set of rules to memorize and regurgitate. It's just really, really fun. It's really fun, and I hope you've all enjoyed it. Oh, but wait a second. Wait a minute. Wait, the end? Wait, I'm forgetting one more thing. Let's play. Gotta play. We gotta play, right? There's an activity associated with this section. I'm excited to work with you on it. Your instructors are excited to work with you on it. So I guess it's not quite the end. The end will come after you do the activity, and then maybe after you watch the supplementary lectures on conics and the law of sines. But thank you again. Thank you again, everybody. I will see you around. I hope I see you in Calc 1 and Calc 2 and Calc 3. I would love it. But that's it. All right, everybody. Take care, and I hope I see you next time.